Okay, so no questions. Let's see. Gracie, do you have any questions? Oh, so she's connecting over audio. 1 second. So, Gracie, do you have any questions before we get started?
No.
Okay. That's a bit little echoey. Okay, so we have chapters 5, 6, and 7 on the test, which equates to modules 8, 9, and 10. So chapter 5 is our thermochemistry chapter. So from our thermochemistry chapter, I'm just going to kind of go over the things you should know and stop me if there's anything you guys need me to go over more in detail. Okay, so for the test, you should know, so this is going to be very little math on this test, right? Just simple math, if any, because all the math was on the take home. But you should definitely know what thermodynamics is and what thermochemistry is and what the difference between the two of them are. So if we're talking about thermodynamics, we're just talking about heat transfer, the study of heat. And then we're talking about thermochemistry, that heat generation during chemical reactions. You should know the definition of electrostatic potential energy. Right, so you should know what electrostatic potential energy is. There is an equation for it. You will not be using this equation, but you should understand what this means. So if we're talking about electrostatic potential energy, we're thinking about our charges of our charged species and the distance of them. So the greater the magnitude of the charge, the closer the distance, the greater the electrostatic potential energy. You should know what your first law of thermodynamics is. So very similar to what we see with the conservation of matter. So energy can be converted from one form to another, but it can neither be created nor destroyed in a chemical reaction. You should know what the system is and what the surroundings are. So our systems, our system is what we are observing. Our surroundings are what's in, it's really surroundings are everything else, but we usually think about the surroundings as things that are in close contact to each other. And since we have the first law of thermodynamics, if we have heat and it's released by our system, which would be a negative Q, then we had to have gotten, or that heat had to have gone somewhere. So it would go into our surroundings with a positive Q. So we have a conservation of energy. Any heat or work done by this or released by the system or done by the system will be absorbed by the surroundings. So our surroundings and our system will have opposite signs for both work and heat. So this is our heat. This is work. We don't look at very much work. We look at mostly heat. Because we're talking about chemical reactions. The only work we really see with chemical reactions is pressure volume work due to gas expansion or contraction. Okay. If we talk about our internal energy, so E is internal energy. It also might be U. But our internal energy is equal to heat plus work. And then if we think about The signs, we should understand the signs of heat, work, and energy. So if we have a Q that is negative, that means heat is released from whatever we're looking at. So if this Q is negative for our system, then heat is released by a reaction. If its Q is negative for a surroundings, then heat was absorbed by our reaction, which would leave it to be a positive. So a positive Q, heat is absorbed. Okay, and then work, if it's negative, heat is, or sorry, not heat, work, sorry about that. Work is done by whatever it is, system or surroundings. And then if it's a positive, work is done on the system or the surroundings, whatever that work is. And then if we have delta E, if it is negative, that means either our Q or our W, either our heat or our work was negative and it was more negative than the other one, or both of them were negative. So it's an overall loss of energy. And we call this exergonic. And then if our delta E is positive, it's an overall gain of energy, either through work, heat, or the combination of both. And we call this endergonic. And you can usually, they put this in the book, but I find it's helpful for me as well, thinking about energy, heat, and work as a bank. So anything that is added to this is a positive, anything that's removed from it is a negative. Now, if we have a, we have two different types of functions. We have state functions and path functions. Those are more definitions you need to know. A state function is a, it's a state that depends only on the initial and final. So it is something that depends on only the initial and final states. So internal energy is a state function. So we can determine internal energy by taking our E final minus our E initial. A path function is going to be something that depends on the path taken. And this is going to include heat and work. These are examples of path functions. And the way I like to think about this, I think work is a really good example of this. So rewrite that, that was horrible. Okay, so this is a mountain. And let's say that there's a hole in this mountain right here. And you can go through the mountain or you can go over the mountain, right? So if you have a little person, and they go up the mountain and then back down the mountain, they end up right here, right? The amount of work is going to be pretty significant if you went all the way over the mountain versus if you go straight through the mountain, right? So this path, much more heat and work are released, done by this person versus the one who goes through, but the initial and final states are the same. Because it depends on the path, one going all the way over versus one going through, we call these path functions. But energy doesn't matter. As long as we know our final and initial states, our change in energy is going to be the same. So we can't do delta Q is equal to Q final minus Q initial. So it doesn't work that way for that. Okay. That brings us to enthalpy. So enthalpy is, well, Q is heat. Enthalpy is heat energy. So we can look at it as enthalpy, which is an H, being equal to our internal energy. So this is our heat plus our work, plus pressure times by volume. So these are all state functions. So volume, pressure, enthalpy, or sorry, volume, pressure, energy are all state functions. Therefore, this is also, enthalpy is also a state function. So we can use delta H is equal to H final minus H initial. So our enthalpy, like I said, this is going to be our heat energy, our internal energy plus any pressure volume. And we are looking at chemical reactions. So the only pressure volume we look at is, or the pressure volume we look at is pressure volume work. Based on gas expansion and contraction. So that is the only work that's going to be done by any of the systems that we're going to look at. Because chemical reactions, if you produce a gas, then if you have that gas, so if you have the reaction in a piston, sorry, I'm a horrible drawer. So if we have a reaction in a piston, it produces a gas. That gas is going to cause an expansion, and it's going to push on, that pressure is going to push on the volume of that gas is going to push on that piston and cause that piston to go up, right? So after, so we have a gas evolution. And because that piston got pushed by that gas, work was done by the reaction. Okay? So we would have a negative W in this case. Okay? And keep in mind, negative W means that our, negative W is coming from the fact that our V final is greater than our V initial. So when we think about our delta V, this is V final minus V initial. So this is going to be, in this case, a positive, right? If we've got an expansion of gas. So our equation, since we have P delta V, in this case, our P, our pressure, is staying constant. Right, so we've got a constant pressure because as the gas expands, it's going to push on that piston and keep the pressure the same. So we've got a constant pressure system. So our P is going to stay the same, but we're going to have a change in volume. So this is going to be our work here. But this needs to be, if we've got an expansion of a gas, this is positive. So we would set it up to a negative. So work will be equal to the negative P delta V. And like I said, this is a constant pressure when we have constant pressure. We can then take that, and if we take our delta H is equal to delta E plus P delta V. So just taking this equation and thinking about it in terms of a change as opposed with a static state. So if we look at our delta H equals delta E plus P delta V, we then put in what delta E is, which is Q plus W. We get delta H is equal to Q plus W plus P delta V. And this is when we were at a constant pressure. So I'm just going to put a little P right there. And then we also know that P delta V is equivalent to negative work. So we're going to put in negative W here. So we get delta H is equal to Q with a constant pressure plus work minus work. And that'll cancel those two terms out. So if we are in a constant pressure system, our enthalpy will equal our heat. Because in this case, the only thing that has work in it is that expansion of that gas. So as long as we have a constant pressure system, our heat will equal our work. And we see this when we think about calorimetry. So if we look at a coffee cup calorimeter, or coffee cup calorimetry, we are solving for Q, right? And then, so it's mass times by our specific heat times by our delta T. So we've looked at this already. And because it's a coffee cup, it's a constant pressure system. Therefore, when we solve for Q here, we are also solving for our enthalpy. Now, as soon as we take it and divide it by moles, at least. And I'll bring some more of that up in just a minute. Okay, so we've got our heat, we've got our enthalpy, or sorry, we've got our enthalpy. Usually when we think about enthalpy, we do enthalpy is equal to the enthalpy of our, or when we look at a change, when we look at a reaction. We take our enthalpy of our products, and we subtract the enthalpy of our reactants. And from this, we can find the enthalpy of a reaction, which is an important function to find. These values will tell us a lot of information about how quickly or how complete a reaction will be. So we're looking at, with delta H, we are really looking at our thermodynamics. So delta E is not really looking at thermodynamics. When we're looking at thermodynamics, we're looking at delta H. So these enthalpy values tells us a lot about how complete a reaction can be. Now, if we have a delta H of reaction that is a negative value, then this is going to be an exothermic process. Exothermic process or reaction. So this is going to be one that generates heat, and we can tell because it is actually hot. So we're going to get an increase of, so this will cause an increase of heat or increase in temperature of the surroundings. Because as it's releasing that heat to the surroundings are going to heat up. So if you've ever had one of those hot packs that you kind of like crunch together, that's usually, you're initiating a reaction, or sometimes it's dissolving a substance. And that process is exothermic, and you feel that heat because of that. Oops, sorry. And then if you have a delta H of reaction that is positive, this is called an endothermic process. or reaction. And this, the reaction absorbs heat. And it's going to absorb that heat from the surroundings. So there's going to be a decrease in temperature of the surroundings. So it'll actually get colder. And again, if you think about a cold pack, there's usually a little snap that you do. And when that occurs, you're going to feel that cold pack get colder. And that usually almost always is just a dissolving process. So dissolving oftentimes can be a endothermic process, oddly enough. I guess up here, I'm just going to, I said reaction is hot, and I meant to say reaction is losing heat. It feels hot because the surroundings are heating up. Okay, so delta H of reaction. One way that we can find the delta H of a reaction is looking at calorimetry. So our calorimetry, that's a measure, so measuring heat flow. And we have QP is equal to mass times by our specific heat times by our delta T. So specific heat it tells us how well something holds on to heat. So greater specific heat it holds on to heat better. And this is going to be in joules over grams times by degrees Celsius. We also may have a molar specific heat or molar heat capacity. In that case, it would be joules over moles times by degrees Celsius. And this equation will change slightly. It'll be QP is equal to moles times by our molar heat capacity times by our change in temperature. So, and sorry, this is specifically coffee cup calorimetry. So here, with coffee cup calorimetry, we are measuring our enthalpy. Okay. Because it is a constant pressure, we just have a coffee cup, right? So the gases that are produced can expand without changing pressure. There's more that I wanted to say about this. What was it? A calorimeter is used. So we have a coffee cup calorimeter. We also have a Bob calorimeter. With a Bob calorimeter, we have a constant volume. So coffee cup, this is constant pressure. But with Bob calorimetry, we are looking at a constant volume. So we're no longer looking at enthalpy. We're actually measuring our internal energy. Okay. Anyways, okay. So in this case, we're measuring our delta E. So if we have, in this case, it'll be Q with a subscript V, that means constant volume. And you don't need to put these subscripts in, by the way. I'm just kind of going through this. You'll still solve for this the same way, right? Although we do need to think about a calorimeter constant here, so we can figure out our Q of our calorimeter by taking the specific heat of our calorimeter times by the change in temperature of our water. And with both of them, keep in mind that a Q of our surroundings is going to be equivalent to the negative Q of our reaction. So whatever we're trying to observe, we're going to actually look at our surroundings to determine our reaction. So in this case, we're usually looking at our Q of our water, because almost all of these, since it's a styrofoam cup, we have to use water. It'll be the negative Q of our reaction. With bomb calorimetry, the Q of our reaction, negative Q of our reaction will be equal to the Q of our water plus the Q of our calorimeter. So we're going to solve for our Q of our water as well. Mass times by specific heat times by delta T. If you are not given water, the calorimeter constant might be taking into account the water already. But anything that I give you, you are going to be required to do both of these. Let's see. What else do I want to say about this? I think that's all I want to say about that. Bomb calorimetry, you should know a little bit about bomb calorimetry and its setup. With bomb calorimetry, this is a, usually it's a way to determine the calories of a food product. So you can combust a food product in a one of these bomb calorimeters to determine how many calories are going to be burned during this reaction. And that is actually going to be equivalent to the kilocalories that you see on the back of a nutrition label, which is big C calories. Okay. Okay. Another way that we can look at, so calorimetry is one way to solve for our enthalpy. Another way of solving for enthalpy is Hess's law. So keeping in mind that enthalpy is a state function, so it doesn't matter how many steps it takes for us to get to our end state. Doesn't matter what path we take, as long as our final and our initial are the same, doesn't matter. So with Hess's law, we do a reaction in a series of steps. And that is how we find the delta H of the reaction. So we kind of sum the steps up and sum our enthalpies up. With Hess's law, you're going to be manipulating equations, and you should know how manipulations of equations within Hess's law are going to affect those enthalpies. So you should know how to explain Hess's law. Another thing we look at, enthalpy of formation. With enthalpy of formation, we're looking at forming a compound, specifically 1 mole of it, using elements. So specifically atoms in their elemental form. So of course, it's good to know what the elemental form of an atom is. If you look at the periodic table, you can generally determine what state different things are in. So if we have things like fluorine and chlorine and oxygen and nitrogen, those are gases. Mercury and bromine are our only 2 liquids. All of our noble, all of our, all of our noble gases are going to be gases as well. Iodine, antimony, selenium, sulfur, phosphorus, carbon, all of our metalloids, and all of our metals, with the exception of mercury, those are all solids. So when we're thinking about those enthalpies of formation, we need our elements in their elemental form. So if we have any metal besides mercury, we'd have that metal and a solid. Mercury would be metal and liquid. And then we have our diatomics. So that's going to be H2 gas, N2 gas, O2 gas, F2 gas, Cl2 gas, Br2 liquid, I2 solid. So those diatomics, there are 7 of them. You should know all 7 of these. And on the periodic table, if you look at the periodic table, you can almost kind of see the 7. So you've got hydrogen over here, which is one of them. So there's 1. And then starting at nitrogen, we got nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And it kind of looks like a little 7. That's how I always remember those. There's 7 of them. 6 of them are in that 7, and then you have hydrogen. So you should know these diatomics because you should be able to write a formation equation for anything. So you've got any of your metals, with the exception of mercury, are going to be in the solid form. Any of your metalloids are going to be solid. And then you've got your gases, again, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Nitrogen, oxygen, fluorine, chlorine, noble gases, and hydrogen are going to be your gases, and then everything else will be your bromine is your solid, and then all the rest of them are liquids. As a note, the delta H, the enthalpy for any thing in its elemental form, is 0. So we have it's 0 for any one of our elements. So O2 has an enthalpy of 0. N2 has an enthalpy of 0. Sodium has an enthalpy of 0. So keep that in mind. You will never have to put enthalpies in for those. So if you're trying to solve using substances, so in the back of the book, if I can find it, I'm looking for it. It's hard to find apparently. I passed it again. Somewhere in the back of the book, and it should also be, here we go. These should also be in the open stacks, but there is an appendix, and it has enthalpy values in here. It's kind of hard to see. These are all formation enthalpies. And if you look at any substance that is elemental in nature, for instance, I don't know if you guys can see this, but we have aluminum solid, and you can't see it, but aluminum solid is the one that has those zeros. So anything in its elemental form will have a 0 enthalpy of formation. But every compound will have an enthalpy of formation that is some value. If it's negative, it's exothermic when it's formed. If it's positive, it's endothermic when it's formed. Okay, and now I just lost my space in the book. Where was I? I feel like I'm spending too much time on chapter 5. We're like 40 minutes in. So yeah, you should be able to write a formation equation. We are not really going to look at bond enthalpy problems until next module. So chapter 8, module 11, I think, 12, module 12. So there will be nothing about bond enthalpies. You should have a general understanding that if you have a single bond, it's going to be longer than a double bond, which is longer than a triple bond. So a triple bond is going to be the smallest. And then energetically, A single bond is going to be the least energetic, the easiest to break. A triple bond is going to be the most energetic, the hardest to break. So that's really all you need to know as far as bond enthalpy. So we want to know bond length versus bond type. And then bond energy or enthalpy versus bond type. Okay. On to chapter number 6. Or module 8, 9. I don't know. Any questions about chapter 5? Module, whatever module this is. This is module 7? Module 7. Any questions about module 7 before I go on to module 8? Or module 8? Module 8. This is module 8. We're going on to module 9, which is chapter 6, if you have the book. So within chapter 6, there is a lot of information in chapter 6, and not a lot of math. So a lot of this in-class portion will come from chapter 6. So you should know the electromagnetic spectrum, and anything that I think I need to go over, like anything I think I need to explain, I will, but if I don't explain it and you need me to, please stop me. So you should know how frequency and energy are related. You should know how frequency and wavelength are related, and you should know how energy and wavelength are related. So these are directly related. Greater frequency, greater energy, and then these are both inversely. So greater wavelength, lower energy, lower frequency. You should be able to use the equations within this module. So that one right there, and this one right here. All right, so these two equations you should be able to use to do some simple math. You should also know that this is called a quanta, right? Quanta of energy. You should know within the electromagnetic spectrum, the things that are in there, what is most energetic and what is least energetic. So we have our gamma rays, and then our X rays, and then our ultraviolet, and then our visible, and then our IR, infrared, and then our microwaves, and then our radio waves. So you should know that gamma rays are the highest energy and radio waves are the lowest energy. Gamma rays are the smallest frequency, highest frequency, smallest wavelength. Radio waves are the lowest frequency, largest wavelength. You should know the three kind of I don't even know how to put this. The three observations, there we go. The three observations that led to the understanding of quantum mechanics. So specifically black body radiation. Black body radiation, a hot substance is going to emit light, and that the wavelength of the light is dependent on temperature. It has nothing to do with intensity. And from here we get, this was determined by Planck's constant, or by Planck. So Planck is the one who determined what was going on here. And he's got his constant, which is at H, which is 6.626 times 10 to the negative 34 joules times by seconds. So he was the first one to really say that that energy increases in a stepwise quantized manner as opposed with continuous. So energy is quantized, not continuous. If it was continuous, then we could just keep on increasing the intensity of something, and that should increase the energy and decrease the wavelength, which is not true. There's also the photoelectric effect. With the photoelectric effect, if you have light shone on a clean metal surface, you will get the ejection of electrons. And this was kind of determined by Einstein. And he also used, so both of them used this equation. So with Planck, he talked about this being a quanta or quantum. And then Einstein said that this was the energy of a photon, where a photon is a packet of energy. So he gave it kind of physical meaning as opposed with just energy. So this led to the idea that radiant energy is quantized. So with this one, what they found is different metals require different frequencies of light to cause the ejection of electrons. And it didn't matter, again, if you change the intensity, so if you change the amount of photons, it still didn't change if a material emitted electrons or not at a specific frequency. So again, if it was based on a continuous energy scale, then you would just be able to add more and more and more photons to eventually get the ejection of electron. But what they found is for every one photon, it excites one electron. So you have to have that energy of that photon be equivalent to the work function in order to get an ejection of electron. And that work function is going to be different based on what material you're observing or studying. So if the energy or frequency is not high enough for that photon, doesn't matter how many you add in there, you're not going to get injections of electrons. The only thing that intensity does, increasing the intensity, which is increasing the number of photons, it only increases the number of electrons if the frequency is high enough. Or, yeah, high enough. And then the last phenomena, I guess, the idea of a line spectra. From excited elements. So they initially saw this with hydrogen. And we saw this when we looked at, when we were looking at the lab last Tuesday. So you see, if you have H2 and it gets excited by passing current through it, it's going to emit light. And that light, when it's passed through a prism, it can be divided into its individual wavelengths. And when we look at this on a spectrometer, we see the 4 lines in the visible region for hydrogen. And they call it a line spectra because they're each lines. So we see this, and initially nobody could really explain what was going on. The first person who tried was Johann Balmer. And he came up with the Balmer equation, which was then further manipulated to give us the Rydberg equation. Which this was able to relate the wavelength of light with an equation. So we have the Rydberg equation specifically for hydrogen. 1 over n1 squared minus 1 over n2 squared. So you could actually fit each of these lines, their wavelengths, into this equation. And there still wasn't really any explanation of what was going on, but they found a mathematical way of describing hydrogen. Then Bohr took this idea and came up with the Bohr model. So the Bohr model took in the idea that energy is quantized, specifically that electrons, their energy is quantized. The idea that electrons can own, and this is the atomic model, sorry, I should have said that. Electrons can only occupy orbits of specific radii, which equates to a specific energy. If they are not in a allowed orbit, so this is going to be an allowed orbit, then the electron will spiral and crash into the nucleus. This allows an electron, or causes an electron to not radiate energy. If it was radiating energy, it would be losing that energy, and it would, again, spiral into the nucleus. And then electrons can only absorb light based on this equation, or energy based on this equation. And we have a 1 photon to 1 electron. And in order to get a electronic transition, we have to go from one allowed energy state into another, and the energy has to be equivalent or equal to or greater than the energy difference between those orbits. And then within hydrogen, he came up with the equation to relate the energies with these, so the energy of the energy levels. So n becomes a principal quantum number. And it describes where an electron is, what energy it's in. Okay, I'm going to go a little bit quicker because now we're almost an hour in. You should know what the ground state is, what the excited state is. You should know what absorption is, excitation, and you should know what emission is. Okay. You should know matter waves. So the idea that matter has waves and its wavelength is equal to h mv. So this is mass times by velocity. This is also known as momentum. So you should know matter waves. And this is de Broglie that brought up the idea of matter waves. And the reason that matter waves come about is he was saying, okay, light can act as a particle. So matter must be able to act like a wave. So the wave-particle duality of light and matter. And using this equation, you can actually get the wavelength of an electron, and it actually does work. Then we have Heisenberg's uncertainty principle. So it basically brings into the idea that if electrons are behaving as waves, then because waves propagate out into space, if we know its energy, we can't precisely know its location. So you can't know location and energy at the same time of an electron. There is a uncertainty with the position once you have the energy. All of these, matter waves, Heisenberg's uncertainty principle, the information that they determined from photoelectric effect and the black body radiation and line spectra, all of this led to the idea of quantum mechanics. And it's essentially treating an electron like a wave. So there are all these equations that, well, there's Schrodinger's equations. Schrodinger is the guy who is responsible for quantum mechanics. Well, one of the guys. But Erwin Schrodinger is responsible for this, and he brought in the idea, his Schrodinger's equations, we call them wave functions. And these wave functions, when they're solved, it will give you a probability, or specifically when we square our wave function. That was not what I meant to do. Take the square of our wave function, we're able to determine a probability of finding an electron based on its energy. So from quantum mechanics, you get your quantum numbers. So you get N, L, M sub L, M sub S. You should be able to solve for all of these. You should be able to determine if a set of quantum numbers is valid or invalid. You should be able to give the quantum numbers for any electron within an atom. And you should also know that the quantum numbers cannot be the same for this. No electron within an atom can have the same set of 4 quantum numbers. So you should know what each of these are: principal quantum number, our angular momentum quantum number, our magnetic quantum number, and our spin magnetic quantum number. And like I said, you should know how to calculate these. You should also know that these will give you information about your shape, so your energy, shape, and your orientation of your orbitals. And these orbitals are different from Bohr. So Bohr just thought about kind of like a planetary model where an electron orbits the nucleus. But with this, we get a probability function. So we have our s orbital, a p orbital, a d orbital, and an f orbital. And these shapes are the probability of finding an electron once we know its energy. You should be able to draw these and again determine what shell, what subshell, what orientation, and the spin of your electron by using your quantum numbers. You should also be able to solve for nodes. So nodes, so these shapes of these orbitals were determined using a wave model of an electron. So literally, when we think about a wave, we're talking about something like this, right? So at these points, we have 0 magnitude. We call that a node. So there's no probability of finding an electron at that point. Every single orbital has at least one node with the exception of s. But as you get higher and higher in energy level, you get more and more nodes, including in the s orbitals. So you should be able to figure out you should be able to solve for radial, your radial nodes and your angular nodes. Okay. You should also understand the Aufbau principle. So how we fill electrons into an energy or electron configuration or orbital diagram. So you should be able to do electron configurations and orbital diagrams. Those were not on the take home. Pretty good indicator that, I mean, these are very important, so they're probably going to be on the test. But you should be able to fill out an orbital diagram or an electron configuration using Aufbau principle. So adding electrons in the lowest energy orbitals first, and then going up in energy until you run out of electrons. So with the Aufbau principle, essentially what occurs is, obviously n equals 1 is lower in energy than n equals 2, which is lower in energy than n equals 3, and so on and so forth. But if we have a many electron atom, so anything besides hydrogen, we have repulsions, and the subshells, the S, the P, and the D and F subshells, they're going to split out within each energy level. And if we're starting here and then they split out, so this is our starting energy and then it splits out in energy, it's going to cause overlap within our electron configuration and within our energies of our orbitals. One way you could solve for that, you could set up this. This is a common way of solving. And it's essentially, you're going to fill in this order. Like that. As a note, you can also use a periodic table to fill out your electron configurations. That would be 1, 2, 3, 4, 5, 6, 7. Three, 4, 5, 6, 4, 5. This is the S. This is the P. So 2, 3, 4, 5, 6, 7. This is a D, and this is the F block. So we have the S block, the D block, the P block, and the F block. And we start at 1 with the S, 2 with the P, 3 with the D, 4 with the F. If you follow that along, you can see exactly where those electrons are going. So if we have something here, its outermost electron is going to be in the 3p orbital. Okay. You should be, like I said, you should be able to do electron configurations. You should also know about the half-filled and full-filled states for transition metals. So stuff like copper and silver and chromium and molybdenum have what we call anomalous electron configurations. So make sure you know why, and you should be able to come up with those. You should also be able to do electron configurations and orbital diagrams for ions. And whenever you're doing it for ions, do your ground state electron configuration first without any difference in electrons, and then remove electrons. And when you remove electrons, remove them from the highest end state first. Okay, chapter 7, or module 10, is our next thing. Does anybody have any questions about this one before I move on? Okay, so chapter 7, just about everything can be related back to effective nuclear charge. So the idea that different electrons have a different pull by the nucleus. So we can actually solve for the pull of an electron by the nucleus just by using this equation. So Z effective is equal to Z minus S, where Z is our atomic number and S is our shielding constant. If we are looking at a simple way, a simple calculation of this, our S will be equivalent to any core electrons. As a note, you should know the difference between core and valence electrons. And you should also know that unless you are actively filling that d orbital, those, or when you're actively filling that d subshell, I guess I should say, those are valence electrons. But if you're not filling that d subshell, they go back to being core electrons.
Professor Foley?
Yeah.
So when we're dealing with ions, is the Z still the atomic number, or is it
Yep.
like of like
We
the element?
never change our Z. That is, our atomic number is always our Z.
Okay, thank you.
No problem. Okay, so a simple calculation of effective nuclear charge, our S is just our core electrons. If we're talking about Slater's rules, our S is equivalent to different values based on whether we are talking about, well, where the electrons are at. So our S is equal to 0.35 for all electrons with the same N value. And this is going to be whatever electron we are observing, and never count the electron we're observing. Our S is equal to 0.85 for all electrons with N equals N minus 1. So whatever you're observing, the N minus 1, that level. So if you're looking at a 5p, then anything in the 4 N equals 4 level will be 0.85. And then S equals 1 for all other electrons smaller, or sorry, in the core, I guess I should say, in the core. So this is going to be N is equal to or less than N minus 2. Okay, so this is going to be, if we're talking about again at 5p, this would be N equals 3, 2, or 1. If we are looking at anything besides a valence electron, we would not include electrons that are in a high, well, we'll never include electrons that are in higher N values. So with this, we'll be able to determine our effective nuclear charge, but you should understand the trend of effective nuclear charge and why. It's very important to understand why. So it increases as we go across our periodic table, and it increases slightly. So there's not much of a change going down the row. So I wouldn't worry about going up or down. but going across. So our Z effective increases as we go across our periodic table. So that trend is going to affect atomic size, which you should be able to describe atomic size. You should be able to describe the trends in atomic radii and ionic radii. Right, so you should understand that. You should know what a bonding, that didn't work, bonding atomic radius is. Okay. You should know the trend in an isoelectronic series. And again, all of this you should be able to relate back to Z effective. Every one of these you should be able to relate back to Z effective. You should be able to talk about ionization energy. What ionization energy is. So the idea, the energy that's required to remove an electron from an atom or ion. So you should know the trend in ionization energy. You should understand when we're going to have large jumps in ionization energy, specifically when we remove core electrons. Removing core electrons is significantly harder than removing valence electrons. And you should be able to relate ionization energy back to Z effective. You should understand the trend in first ionization energy. So in general, it increases as we go across the periodic table and increases as we go up the periodic table. There are some anomalies, stuff like aluminum, stuff like oxygen. You should understand why those anomalies exist, and we can think about half-filled and full-filled states again here. I forgot to mention this in the last chapter, and I'm so sorry. I wish I had remembered. You should also know what the Pauli exclusion principle is, and the Hund's rule. So you should be able to define both of those, and you should be able to relate how they are seen within an electron configuration or orbital diagram. So what consequences do these have on electron configurations and orbital diagrams? Okay, sorry, back to first ionization energy. So you should know trends in first ionization energy and when you have anomalies. So when there are anomalies and why. You should know what electron affinity is. So if we think about the idea of electron affinity, it's an affinity that an atom has for an electron. You should know the general trends. So electron affinity is generally negative as opposed with positive for ionization energy because it is affinity, right? It's becoming more energetically stable, which is why it's a release of energy when we add the first electron. We do not see, so when we think about our main group elements, and that's really the only ones we're going to look at electron affinities for, but generally our metals are going to have greater negative electron affinities. And then anything that we're going to add into new states, so our noble gases, we'd be adding into a new N value by adding electrons, so it's going to have a positive electron affinity. Group 5A, nitrogen is anomalous because we have a half-filled state and we're going to no longer have a half-filled state. Group 2A generally has positive electron affinities because we're going to add into a new subshell. So keep in mind where anomalies exist in electron affinity and why they exist. You should also know properties of metals. nonmetals, and metalloids. So you should be able to give me properties of these. So the idea of metallic character, you should be able to define metallic character and give the trend. And again, relate it all back to our Z effective. You should know in some general information about the following groups. So you should have group info for alkali metals, alkaline earth metals, the oxygen group, often called the chalcogenides. Oh my God. And then the halogen group. And the noble gases. So you should understand what properties these have and how those properties change as we go down the group. So alkali metals, alkaline earth metals, they're both very reactive to oxygen and water, and that reactivity increases as we go down the table. They're relatively low densities for both of them, but again, they increase as we go down the table. The ionization energies, very low for our alkali metals, reasonably low for our alkaline earth metals, but those ionization energies go down as we go down the periodic table. With our with our oxygen group, this is the only group that we have, or the group that we have a lot of allotropes in. So oxygen has allotropes, sulfur has allotropes, selenium has allotropes, and tellurium has allotropes, which is kind of interesting. The melting point increases as we go down the periodic table. The density increases as we go down the periodic table, so you should know stuff like that. And then with our halogens, this is the only group that we see all three states in. So when we have fluorine and chlorine, those are in the gas state. Bromine is in the liquid state. And then iodine and antimony are in the solid state. And this is the only group that occurs. As we go down our halogen group, first of all, our ionization energies are reasonably large. They want to gain electrons, so they have very negative electron affinities. And yeah, so they, by the way, halogen means salt forming. So they all want to form salts. They prefer to be in an ion state. And then our noble gases, they are very unreactive. They have very high ionization energies. It does decrease as you go down the group. But it's not until we get to krypton that we actually get to something that will produce a compound. And krypton only has one stable compound, or one compound, I don't even know if it's stable. Xenon has a couple compounds, and then radon is too radioactive to really look at compounds. But they generally don't make compounds, right? Because they are an inert group, because they follow the octet rule, which we'll talk about more next module, and they're really happy. Okay. Any questions? I went pretty quickly through that last module because it is mostly read and kind of retain.
Dr. Foley, I have a quick question. I'm sorry. So I didn't get the take home last week, and oh, it's Olivia, by the way, and I tried to email you, but I think my computer's been acting funny, and I don't know if it's sent or not. But
I
I
did
can
not get
write
that
down
email.
the questions. Is that okay?
Could you possibly convert it onto a test tomorrow if I give you a take-home test?
Yeah, if I write it down here, I can transfer it tomorrow.
Okay,
Thank you.
thank you. Okay, any other questions? Okay, if there are no questions, we are good. I will see you guys tomorrow morning for our test. If you have any questions, please send me an email and I will see you guys later.